Lecture 4.2, Estimation of Sample Mean and Variance. This is in Dane's wheelhouse right here. Dane really gets this material, I think.
Oh, yeah.
Yeah. Okay. The mean is estimation and sample statistics. The mean and variance definitions from lectures 3.7 and 3.8 apply only to a random variable for which we have a theoretical probability distribution, right? They were defined as being the expectation, etc. Second central moment. Typically, it is not until after having performed many measurements of a random variable that we can assign a good distribution model. Until then, measurements can help us estimate aspects of the data. We usually start by estimating basic parameters such as mean and variance before estimating a probability distribution. There are two key aspects to randomness in the measurement of a random variable. First, of course, there is the underlying randomness with its probability distribution, mean, standard deviation, etc., which we call the population statistics. Second, there is the statistical variability that is due to the fact that we are estimating the random variable's statistics, called its sample statistics, from some sample. Statistical variability is decreased with greater sample size and number of samples, whereas the underlying randomness of the random variable does not decrease. Instead, our estimates of its probability distribution and statistics improve. So you can imagine, like if you're measuring a noisy voltage signal, you could measure that signal forever and it's still going to be just as random as it was. You can take as many samples as you want, and that underlying process of noise is just going to be there, right? You aren't going to change that fact by taking a bunch of samples. But you can come up with a better and better estimate of, say, the mean and the variance, etc., of that underlying process that is random. So you can get a better and better estimate of it. You can think of the statistical variability, the randomness that comes from the statistical sampling, to get less and less because you're going to be getting a better and better well, sample is an overused term here, but a better and better sample of what is actually going on. So less and less of your variability will be coming from the statistical aspect of it, and more of it will be coming just from the underlying process. We don't really need two of me up there. One of me is plenty. Okay, sample mean, variance, and standard deviation. The arithmetic mean or sample mean of a measurand with sample size n represented by a random variable x is defined as x bar, which is the division of the sum of all of the samples, or the sum across the sample of all of the values of x divided by the number of samples. You guys have been computing this for a long time, okay? If the sample size is large, the sample mean approaches the population mean or the mean. The population mean is another name for the mean, which is equal to the limit. If you take the sample size to infinity, you'll approach the population mean. Yes?
So is M the same thing as mu in the book?
Yeah, so I am a little bit inconsistent with mu and m. Mu is the one that we use especially for Gaussian, because the Gaussian mean parameter is often taken to be mu, which is the mean in our expectation definition of it. I try to use m, but occasionally I will slip up and use mu, which is just another notation for it. So mu and m are taken to be the population mean. I mostly use m, but occasionally I'll slip up and use mu. So, great. I tried to go through this time and fix all those, but I think there are still a couple remaining. Recall that the definition of the mean is the expected value of x. The sample variance And, the sample variance of a measure and represented by random variable x is defined as being the difference of each value of x from the sample mean squared. So you're taking the square of the differences of the sample value from the sample mean. And you're summing those up and dividing by n minus 1, the sample size minus 1. If the sample size is large, the sample variance approaches the variance. The population variance is another term for the variance and can be expressed as being the limit as you take the sample size to infinity of the sample variance. Recall that the definition of variance is the second central moment of the random variable. The sample standard deviation of a measure and, represented by random variable x, is defined as the square root of the sample variance. If the sample size is large, we'll get the sample standard deviation approaching the population standard deviation, which is the limit as you take the sample size to infinity of the sample standard deviation. Recall that the definition is the square root of the population variance. Sample statistics as random variables. There is an ambiguity in our usage of the term sample. It can mean just one measurement, or it can mean a collection of measurements gathered together. Hopefully it is clear from context. So sometimes we'll say a sample, and we mean a single measurement or a single data point or a single value of something. Other times we mean an entire collection of measurements or of values. It is sometimes hard to tell which one's being referred to, but hopefully from context you'll see. In the latter sense, meaning a sample being the entire collection, being an entire collection of measurements, often we collect multiple samples, each of which has its own sample mean and standard deviation. Okay, so you can think of us taking like multiple batches. So in this case, we're calling a sample one of those batches. So you might take multiple batches of measurements, okay? And we'll call those batches samples. So it'll have a sample mean and a sample standard deviation. So each one of them will have that. In this situation, the sample mean of the ith sample and the sample standard deviation of the ith sample are themselves random variables. It's very meta, okay? So the mean and standard deviation are themselves random variables. This means they have their own sample means and standard deviations. Okay, so you can take the standard deviation of the means.
Mean of the mean and standard deviation of the standard deviation.
And you take the standard deviation of the standard deviation. You take the mean of the mean of the standard deviations, the standard deviation of the means, and the standard deviation of the standard deviations. Okay, I know. And you might think, this is just crazy talk right here. Okay, it's like, yeah, you could, but when would you? You do a lot, actually, it turns out. This is actually the most common way to represent data using error bars is to actually use the standard deviation of the means. Okay. And I've seen this taught a lot, and it usually is just like handed down from someone, from the stars, from the clouds to us. That you make the error bars the standard deviation of the means, and what is that? Well, it's just the standard deviation, sample standard deviation divided by the square root of n. No questions further shall be asked or answered. And so I like to actually get into what that means. Like why is that? Because it bothered me, and I never liked it until I actually understood it. So yeah. So the mean of means, which is the x bar, is equivalent to a mean with a larger sample size, and is therefore our best estimate of the mean of the underlying random process. Okay, so the mean of means is our best estimate of the mean of the underlying random process. The mean of standard deviations is our best estimate of the standard deviation of the underlying random process. Okay, so that makes sense. Like, you're estimating the mean and you're estimating the standard deviation, and so if you take the mean and the mean standard deviation, you're getting the best representation you have of those. Okay, the standard deviation of means is a measure of the spread in our estimates of the mean. It is our best estimate of the standard deviation of the statistical variation and should therefore tend to 0 as sample size and number of samples increases. Okay? So that is something that we have this idea that something should shrink as we measure more and more, right? Our error bar should really shrink our estimate of something more and more, this is, this is the statistical spread part that should shrink. Okay, the standard deviation of standard deviations, which is that, an unprecedented 3 levels deep subscript situation, is a measure of the spread in our estimates of the standard deviation of the underlying process, which is fun. It should also tend to 0 as sample size and number of samples increases. Okay, so which of these do you think should be our error bar? I know I mentioned it earlier, but...
Standard deviation means?
Yeah, the standard deviation of the means, because this is the thing that shrinks. The more and more we measure this, the better and better estimate of what this mean is. Okay? So we really want an error bar that the better and better we have an estimate of it, the tighter and tighter our error bar gets. We're not trying to represent the variation of the underlying random process. I mean, that could be a situation that we have, and if that was the situation, we would be representing the mean of standard deviations. But typically, we're trying to represent how well do we know that data point that we have error bars on. And we know that mean, which is the data point, to the level that we have the standard deviation of the means error bar. Okay, that error bar should be a representation of how well we've estimated that mean. What is the spread in our estimation of that mean? And that's why we use as our error bar the standard deviation of the means. Okay, it's a good one. Okay, let n be the size of each sample. Okay, so n measurements in a sample. So this is the sample in the sense of having a batch of measurements. It can be shown that the standard deviation of the means can be estimated from a single sample standard deviation. So you take that single sample standard deviation and you divide it by the square root of the sample size. Okay? This shows that as the sample size n increases, the statistical variability of the mean decreases, and in the limit approaches 0. So this is the error bar, and what's cool about it is that this is approximately true. So you don't necessarily have to take a bunch of samples, you don't have to take a bunch of batches in order to come up with the standard deviation of the means. You can estimate it using equation 4.7 from a single sample, from a single batch of measurements.
Just divided by square root of n.
Yeah, so the number of measurements in that sample size.
So the only requirement is that n must be big enough to make this.
Yeah, so you want n to be, the bigger you make n, the larger you make your sample size, the tighter your error bars are going to get, which is exactly what you want, right? I mean, you take, and it makes sense, right? The larger the sample size, the better and better your estimate of the mean will be. So, excellent. So hopefully there was a lot of fogginess around error bars and standard deviations and which values they were for me before I realized that we were talking about different things and that there were standard deviations, sample standard deviations of the mean, sample standard deviations of the standard deviation, and like there were like standard deviations of things and what those all really meant. Took me a while before I like understood that, and I now every time I teach anything to do with statistics, I always like pound on this because I think it's so important. So this is my little soapbox. Non-stationary signal statistics. Okay, so now I'm going to take us to the next sort of level deep here. So the sample mean variance and standard deviation definitions above assume the random process is stationary. Okay, that is, its population mean does not vary with time. That's true for a lot of things. We're just trying to measure one thing, like what is the temperature in this room? That never changes. It's just one thing, right? So that's okay. However, a great many measurement signals have populations that do vary with time. In other words, they are non-stationary. Sometimes the non-stationarity arises from a drift in the DC value of a signal or some other slowly changing variable. But dynamic signals can also change in a recognizable and predictable manner, as when, say, the temperature of a room changes when a window is opened or when a water level changes with the tide. Okay, so the one would be a sudden change in one direction. The other one would be a sort of, water level changing with time would be sort of cyclic. Okay. Typically, we would like to minimize the effect of non-stationarity on the signal statistics. In certain cases, such as drift, the variation is a nuisance only, but other times it is the point of the measurement. Sometimes you're trying to measure that changing process, like if you're trying to measure the motion of something, that would be something that changes, and so you can't just try to get rid of that part of the signal. You're not trying to get rid of that change. That's the part that you want to measure. Okay? Two common techniques are used, depending on the overall type of non-stationarity. If it is a periodic non-stationarity with some known or estimated period, the measurement data series can be folded or reshaped such that the ith measurement of each period corresponds to the ith measurement of all other periods. Okay? In this case, somewhat counterintuitively, we can consider the ith measurement to correspond to a sample size n, where n is the number of periods over which measurements are made. So you can think of, imagine you have a lot of data points along a signal that repeats this over and over again with some noise on it, right? So it's periodic, and in time it goes to the right, but I'm just going to say we had multiple periods of it, and we took them, instead of having them be in time that way, we just take each one, we chop it, and we put it like this, and we say, okay, the ith data point in for each of these is approximately is a measurement of approximately the same thing. Okay, so if you keep doing this, you keep measuring this repeated signal over and over and over again. You're saying, okay, I'm measuring the same underlying signal. The fifth data point for each of these periods is corresponding to the same thing I'm trying to measure. Maybe it's a voltage, maybe it's a velocity, whatever it is. And you can take the collection of the fifth, say, the nth, or the ith, I guess I said, of those ith ones, and treat them as a sample for estimating that variable at that moment in the period, in the cycle. Okay? So this would be I equals 1, I equals 2, I equals 3, all the way down to n. Okay? So that's a pretty good scheme, especially if you're doing an experiment that you can repeat the cycle over and over and over again. That's how we make these measurements. Is we just repeat it. We take this, data points at the same moments in time, and then we repeat the same thing. We do it again and again. In the lab, when you guys were in the ME316 lab, you guys did this with an RC circuit where we put in a square wave, and we saw the signal respond, charge up the capacitor, and then discharge the capacitor, charge up the capacitor, discharge the capacitor, etc. Just keep doing that, right? And we just took multiple periods of that periodic signal, and then we just cut them up, and then we just chopped them into bits, where we said this period is like the first sample for each of these, the first value for each of these samples, and then the next one, etc. So we did that in that lab, and that's usually the best way to do it if you can do it. If you can repeat the same thing over and over again and measure it multiple times, that's the best way to do it. And then you treat each of the data points at that given moment of time, or at that ith data point, as being part of the same measurement, of the same value. Okay. There are all kinds of issues that come up when you start talking about how do you make sure that you get it at the right moment in the period every time. You have to really work on timing here, right? Because if your data points get off by a little bit for the period, you're not, the fifth data point doesn't correspond to the same part in the period. So you have to get your timing right. But if you have it all electronically controlled, you should be able to get the timing right. So, great. Here we go. So when the signal is aperiodic, we often simply divide it into small, relative to its overall trend, intervals, over which statistics are computed separately. So we could just chunk this thing into say, okay, if we just took maybe it's something that changes, we only have one shot measuring this thing, and it looks like that. Hopefully we have, if you zoom in on this little bit here, you expand it out, hopefully you have a bunch of data points in here that you could average over a small chunk and use as your sort of mean value. So you could get a little bit of smoothing here. You could also run it through a smoothing filter. That's another way to do it. But you wouldn't be able to estimate your measurement of that line in terms of your error bars or anything. It's not ideal to have just one-shot measurements of things. It's ideal to have repetition of it. So ideally, we create a periodic system measurement, even if it's not naturally periodic. Maybe we take a measurement and then we wait, and then we take another measurement when it comes back around or whatever. So we try to force it to be periodic so we get a sample that's significant. Okay. Note that in this discussion, we have assumed that the non-stationarity of the signal is due to a variable that is deterministic and not random. So if it's a random variable that's changing the underlying process, then you've got bigger problems on your hand. So, yeah. Okay. Here's an example. Measurement of Gaussian noise on non-stationary signal. Consider the measurement of the temperature inside a desktop computer chassis via an inexpensive thermistor, which is a resistor that changes resistance with temperature. The processor and power supply heat the chassis in a manner that depends on processing demand. For the test protocol, the processors are cycled sinusoidally through processing power levels at a frequency of 50 millihertz for NT equals 12 periods and sampled at 1 hertz. Assume a temperature fluctuation between about 20 and 50 Celsius and Gaussian noise with standard deviation 4 Celsius. Consider a sample to be the multiple measurements of a single instant in the period. So we're doing like that periodic scheme here, where we're going to have this repetition, we're going to take multiple cycles and average them. Generate and plot simulated temperature data as a time series and as a histogram of frequency distribution. Comment on why the frequency distribution sucks. 2, compute the sample mean and standard deviation for each sample in the cycle. 3, subtract the mean from each sample in the period such that each sample distribution is centered at 0. Plot the composite frequency distribution of all samples together. This represents our best estimate of the frequency distribution of the underlying process. 4, plot a comparison of the theoretical mean, which is 35, and the sample mean of means with an error bar. Vary the number of samples and comment on its effect on the estimate. 5, plot a comparison of the theoretical standard deviation and the sample mean of sample standard deviations with an error bar. Vary the number of samples and comment on the effect. Plot the sample means over a single period with error bars of plus or minus 1 sample standard deviation of the means. This represents our best estimate of the sinusoidal heating temperature. Vary the number of samples and comment on the estimate. We'll do it in MATLAB. We generate it using rand_n, which gives us a Gaussian distribution of our that's going to represent the sort of the noise on the signal. So it was a Gaussian random variable. So we're going to have a signal and noise, and this is what we've got. So this is the raw data, just plotted through time. We heat it up and then cool it. We heat it. We cool it. Heat it. So we get this temperature fluctuation. What we're trying to do here is measure this underlying sinusoid. Okay? So if you want to measure what is the underlying sinusoid here, we don't really want to get an average of this whole thing. If you just average the whole thing, that's just what is the mean of this whole thing. It's not really what we're looking for, right? And so if you look at like a frequency distribution, you see this non-stationary signal that's it's sweeping back and forth, and there's noise on top of it. We're not really getting a frequency distribution that's associated with the noise. We're getting a frequency distribution that's associated with the noise and the underlying non-stationary process. So what we do is we reshape it, and we create, there are 12 periods, so we create 12 cycles, and I think we call those rows. So there's 12 rows, and we take those 12 rows, and we create each of the columns being a sample associated with that moment in time. And we look at the composite frequency distribution, for which we subtract out the mean. So that non-stationary signal, each sample had a mean associated with it. So we subtract out that mean, we should have left just the noise that's left. So I mean approximately, right? Approximately just the noise that's left. We look at that frequency distribution, and we actually estimate what the probability density function is from the data, which you can do in MATLAB using this PDF fitting process, so fit distribution, which is a nice little tool. So you can say, what is the approximate probability density function, assuming it's normal or Gaussian, and it'll give you that model. So I plotted the dashed green one. The dashed green one is the probability density function that we use to generate this noisy data. So we got pretty close to backing out exactly what the probability density function was that went in based on this estimate, which was pretty cool. It's nice to be able to see we can estimate what that probability density function is. And we compare the means. So the mean of means is right around 35. So that makes sense, right? That's theoretically what should be in the middle here, halfway between 20 and 50. And then we have the standard deviation of the means. And this is estimated by using that equation, right? We take the mean of the standard deviations, and that's our best estimate of the standard deviation. And we take the square root of nt, and that gives us standard deviation of the means. So we do something similar with the standard deviations as well. And we see the mean of means is 35.1 or whatever. And the standard deviation of the means is about 4. So that's the error bar, plus or minus 4. The standard deviation, so the mean of standard deviations is plotted, and then the standard deviation of standard deviations is the error bar on it. Okay? Now we want to plot one cycle here, and we want to plot the standard deviation of the means for each sample for that part of the period, right? So for the peak, for instance, at like 5 seconds into each period, we have multiple measurements of that point, and that is represented by this data point here and the error bar on top. So the population mean was the underlying sinusoid, so I plotted that in red, and then I plotted the sample mean with the one standard deviation error bars there. And as we increase the sample size here, those error bars are going to get tighter and tighter and tighter, and you're going to approach this population mean line more and more and more. Okay, so that's how to so what we did is we created data by randomly generating noise on top of a signal, and then we started to try to estimate what we used to generate it. So we packed it in, and then we unpacked it. So yeah, but if you just had measurement data, you could unpack it. You don't have to start with randomly generated data. Okay, good. Any questions on this stuff? I think this stuff is super practical. When you do any sort of measurements, take any experiments, this is the type of thing that you're going to need to do with it to represent it well, to publish it, or to have any confidence in what's going on. Okay? All right.